All right, good day to each and every one of you, and welcome back to another lecture video discussion. So for today's video we will be discussing all about thermodynamic processes and also the first law of thermodynamics. Now the outline of this lesson is, first we will discuss the internal energy of a system, and also the second one is we will explain the different thermodynamic processes. Number one, we have the isothermal process, we have the adiabatic process, the isobaric process, and we also have the isochoric process. So we will explain that later on. Okay, so now let's start with the internal energy of a system. Now if we will define internal energy or a capital letter U, the variable for internal energy is capital letter U, is the total energy contained within a thermodynamic system. So the internal energy contains, or it includes, number one, the kinetic energy of the molecules, which is due to the motion of the molecules, and we also have the potential energy from intermolecular forces. Okay. Now, in thermodynamics, we mostly consider changes in the internal energy. So, change in internal energy, we have delta U, not absolute values. So, it is governed by the first law of thermodynamics. So, now the first law of thermodynamics is a statement of energy conservation. So, in thermodynamic na system. So, it says that we have here an equation. This is the equation for the first law of thermodynamics. We have delta U, or the change in internal energy, is equal to, our Q here is the heat minus, or the heat added to the system, minus W is the work done by the system. So again, the delta U is equal to Q minus W, or the change in internal energy is equal to the heat added to the system minus the work done by the system. Okay, now let's go to the thermodynamic processes. So again, we have four thermodynamic processes. We have the isothermal, adiabatic, we have the isobaric, and isochoric. Now we will discuss each of that process. Okay. Now let's go to the isothermal process. Now in isothermal process, we have delta T is equal to 0, or the temperature is constant. Now, since the internal energy depends on temperature, now the internal energy, since delta T is equal to 0, so also our delta U, or the change in internal energy, is also 0. Okay, so now from the first law of thermodynamics, diba, again, the formula of first law of thermodynamics, we have delta U is equal to Q minus W. So if delta U is equal to 0, so it means that, if it is equal to 0, so it means that Q is equal to W, or the heat added to the system is just equal to the work done by the system, or the heat added is entirely converted to work done by the system, or vice versa. Okay, so example, slow compression, expansion of gas in contact with the thermal reservoir. Now, as you have noticed here on the left side, we have a graph, a PV diagram. So this is what we call the PV diagram. So on a PV diagram, see, isothermal is a hyperbola, or a curved line. So we have the red broken line here nga naka-curve. So this is the PV diagram of the isothermal process. So again, PV is pressure and we have the volume. So PV diagram. So since delta T is 0, so ang isothermal is a hyperbola, or it is a curved line. Okay, now let's go to the second one. We are done with the isothermal. Now let's proceed to the adiabatic process. So in adiabatic process, Q is equal to 0, or walang heat exchange with the surroundings. So no heat exchange with the surroundings, and all energy changes go into work. So since Q is equal to 0, again, if we will go back to the first law of thermodynamics, delta U is equal to Q minus W. So if Q is equal to 0, so delta U is just equal to the negative of the work done. Now, what does it mean? Now, if the system does work, now its internal energy decreases. Okay, negative work man. Ang change in internal energy is just equal to the negative of the work. So, meaning, kung if the system does work, then the internal energy decreases and also the temperature drops. Now, if work is done on the system, its internal energy will increase. So, therefore, the temperature will rise. So, we have fast compression or expansion where no time for heat exchange. So, again, we have also here on the PV diagram. So, the same PV diagram that we saw on the isothermal. But here, the adiabatic is also a curve. So, this is the blue one. So, this is the curve of the adiabatic, but steeper than the isothermal na curve. Okay. So, we are done with isothermal and adiabatic. Now, let's proceed to the third one. See, isobaric. Okay, isobaric means that the pressure is constant or pressure remains constant. So, but the volume and the temperature may change. So, we have the work done. If we will have the formula for the work done, it is expressed as work is equal to pressure times the change in volume. So now, what will happen to the first law of thermodynamics? From the first law, we have delta U is equal to Q minus W. Now, if we will substitute work with P times delta V, it becomes delta U is equal to Q minus P times delta V. Okay, so this is now our first law of thermodynamics na formula by using the formula for the work done in terms of pressure and volume. Now, the heat added goes to the increasing internal energy, and also it goes to doing work or expanding the gas. So, the internal energy changes with heat and also volume. So, on the graph, we can saw that isobaric, since constant man ang pressure, so isobaric is just a horizontal line on the PV diagram. So, constant si pressure. Wala ga increase, wala ga decrease, it's constant. So, it is a straight, a horizontal na broken line, kaning green broken line. So, that is isobaric. And then, we have, let's go to the fourth one, we have the isochoric process. Kung si isobaric is constant pressure, si isochoric is constant ang volume. Okay, the volume remains constant, so therefore, no work is done or zero ang work. Okay, so now, ang first law, from the original formula of first law, delta U is equal to Q minus work. So, since work is 0, so delta U is just equal to Q. Or, all the heat added to the system will increase the internal energy and also the temperature of the system. Okay, so on the PV diagram, si isochoric, kay constant man ang volume, so we have here this one. The black nga broken line nga naka-vertical. So that is the graph of the isochoric process, because again, the volume doesn't change or the volume is constant. Okay, so we are done explaining those four thermodynamic processes. Now, let's sum them up. Okay, so we have isothermal, adiabatic, isobaric, and isochoric. So, si isothermal is constant temperature. Adiabatic is the heat is equal to 0. Isobaric is constant pressure and isochoric is constant in volume. Okay, so we have here the heat, if it is equal or not equal to 0, the work done, and also the change in the internal energy. Okay, now let's try to solve some examples regarding with the thermodynamic processes. Okay, now we have here a problem. Problem number 1 is all about isobaric expansion. Now our problem here is a gas expands from 2 liters to 5 liters at a constant pressure, okay, of 100 kilopascals. So the gas absorbs 500 joules of heat. Now we need to find, letter A, the work done, and letter B, so this is capital letter W, and letter B is the change in internal energy, or delta U. Okay, so we will solve each of this one. So let's have first our given. Okay, so I think color red is a little bit masakit sa mata, so let's try to change it with another color. So our given is, we have the volume. So we have the initial volume, VI is 2 liters. Our final volume is 5 liters. We also have the pressure. Pressure is 100 kilopascals. And we have the work done. I mean heat, sorry. Heat is 500 joules. Okay. Now for letter A is we need to solve for the work done. Now if you can still remember, ang given lang nato is the initial and final volumes, the constant pressure, and the heat. So in order for us to solve for work is we will use the formula of work, which is work is equal to pressure times delta V, or pressure times final volume minus initial volume. Okay, so we have here 100 kilopascals times 5 liters minus 2 liters. Okay, so 100 kilopascals is equal to 100,000 pascals times, we have 5 minus 2 liters is 3. So 3. Now, this is 3 liters. So if you will convert that into cubic meters, so 3 liters is just equal to 3 times 10 to the power of negative 3 cubic meters. So we will use cubic meters here instead of liters. Okay, so we have 3 times 10 to the power of negative 3 cubic meters, so that ang ato ang unit will be in terms of joules. So 100,000 times 3 times 10 to the power of negative 3. So if we will calculate that one, we will arrive with 300 joules. So the work done by the gas is equal to 300 joules. Okay, so we are done with letter A. Now let's proceed with letter B. So sa letter B is we will solve for the change in the internal energy. So for the change in internal energy is we will use the first law of thermodynamics. So since naman tayo given heat, and also we already solved the work done, so we can solve for the change in internal energy. So delta U is equal to Q minus W. So we have 500 joules minus 300 joules. So 500 minus 300 is just equal to 200 joules. Okay, so we are done solving problem number 1. So I hope you understand, or you understood on how to get the work done, or how to solve the work done, and also the change in internal energy. Now, we have here another problem, problem number 2, which is all about isochoric. So isochoric is, if you can still remember what is isochoric, Isochoric is constant volume. Okay, now we have here a gas in a rigid container, so the volume is constant, receives 150 joules of heat. Okay, so let's write the given here. Yun na lang sa ubos. Given, we have the heat is 150 joules. So what is the change in internal energy and the work done? Okay, so duha ka buok. Change in internal energy, so we need to find delta U and also the work done. Okay, now since volume is constant, if you can still remember in isochoric, volume is constant, so work done is equal to 0. So if work done is equal to 0, from the first law of thermodynamics, delta U is equal to Q minus W. So our work is 0, so delta U is just equal to the heat. Okay, heat. So we have the heat is 150 joules, so it means that delta U, or the change in internal energy, is also equal to 150 joules. Okay, did you understand? So as long as you remember the different thermodynamic processes, I think it's a little bit easier in solving problems like this one, because if you cannot remember when V is constant, work is equal to 0, if you cannot remember that, then how can you solve for the change in internal energy and also the work done? Okay, so again, we must remember every detail of each thermodynamic processes. Okay, so I think that's it for this lecture video, and also thank you very much for listening, and I hope you understand, or I hope you understood something out of this lecture video discussion. So I think we'll see you again on our next lecture video. So thank you very much for listening. Bye.